Thanks for the introduction. Thanks for the greetings. Welcome to our last talk in this Data Fest, and I know that the efforts required to attend the last talk in any event are, well, extremely high, so I'm very grateful that you found strength to attend to my talk. So I will present a presentation about our most recent results. So in some sense, this is still a work in progress. However, I personally find it quite interesting, and hopefully you will also agree with me that this is not absolutely useless results. So what was our motivation? We all know that modern deep neural networks lack interpretability. So they do train, but the processes that happen during their training are still quite poorly understood. On the other hand, we have many different disciplines where similar processes arises, and for which the scientists already know how to explore them. So maybe it will be possible to build a kind of bridge between different disciplines. And in this particular talk, we'll try to bridge the gap between training dynamics in deep neural networks and, surprisingly, thermodynamics. So the more concrete motivation is following. So imagine that we have a standard deep neural network, and we're training it using stochastic gradient descent with a constant learning rate. So then, if we monitor the training loss with respect to epochs, first it goes down, and at some point it stabilizes. And if it deviates by a little to the above, then it will be reduced after a while. If it goes down, it will be increased after a while. So it looks like there exists some kind of attractive force that attracts our training loss to this particular level. And this level depends on the choice of the learning rate. So if we reduce the learning rate, our training loss will behave as follows. So it starts decreasing again, and then it will stabilize at a different level. If we, for example, after that, will increase the learning rate to the initial value, our training loss will go up and stabilize at the previous level. So there's a kind of attractor which defines the behavior of the training loss. But if there's an attractor or a negative feedback loop, this means that we can define a different objective that is minimized during the process of SGT training with a given learning rate. And so our goal will be to define this objective. So it happens that we're trying to minimize training loss, but we're using SGD with a fixed learning rate, and it appears that this process minimizes a different objective, not the training loss, but something different. And surprisingly, this something different arises from thermodynamics. So the rest of my talk will be as following. So first, we'll give some recap of thermodynamics, some facts that you probably still remember from high school. Then we'll consider what happens when we start stochastic optimization of so-called scale invariant functions. And training losses in modern deep neural networks are almost fully, or at least partly, scale invariant. And finally, we'll discuss some equilibrium states that appear in deep neural networks. So what is thermodynamics? Thermodynamics is a subfield of physics which studies the behavior of thermodynamical systems under thermal fluctuations. So when we have non-zero temperature, our particles oscillate or fluctuate, and thermodynamics studies how they do this and what are the properties of equilibrium or steady state of thermodynamical system. So here and after, we'll consider just thermodynamical systems which consist of just a gas. So the simplest thermodynamical system. So gas is a set of molecules. The molecules are moving, so they have some energy. And any molecule is described by so-called microscopic variable. That is simply its coordinate and its momentum. But there are myriads of those molecules, so it's absolutely impossible to describe any of them in detail. And in thermodynamics, as well as in statistical physics, the people are usually using the distribution of Z. So instead of considering each particular Z, so for each molecule, its coordinate and its momentum, the physicists simply state that there exists some distribution, rho of Z, and the parameters of any molecule is simply a sample from this distribution. So the distribution itself may evolve in time. So for example, we may consider, say, a balloon with a gas with some initial coordinates and the momentums, and then run the thermodynamical evolution. And during this evolution, the system will evolve from initial state to some stationary state. And after stationary or steady state is reached, the evolution stops. So the system continues fluctuating, but nothing changed globally. So the distribution rho of z stops changing. In some sense, this looks like the system is dead, because nothing is evolved anymore. And the goal of thermodynamics is to study first how the thermodynamical system evolves to the steady state and what are the characteristics of the steady state itself. And surprisingly, as we'll see later, it appears that there are many, many similarities with the training process of deep neural networks. Okay. Yeah. So since the description of each particular molecule is impossible because there are myriads of them, and we deal with just probabilistic distribution in this space of possible coordinates and momentums, thermodynamics deals instead with so-called macroscopic variables. So these are variables that can be easily measured if we know the distribution rho. And among those variables, there are, first of all, the mean internal energy. So as I thought, each configuration of molecules has energy U of z. So if the molecules are distributed according to the distribution rho, then we can compute the mean energy. And this I will denote as U bar. So mean internal energy. Also, we can compute temperature, volume, and pressure. This is something easily measurable just by using some devices like thermometer or manometer, whatever. And finally, we may also compute the entropy of distribution rho. So these are microscopic variables that can be measured, and the goal is to understand how those variables change when the system evolves to the steady state. And this is well-known ideal gas law. So please raise the hands, those of you who remember this equation from school. So many of you, great. It simply states that in ideal gas, pressure times volume over temperature is always constant. It was first discovered empirically, and later it was, well, justified from some postulates of a molecular kinetic theory. So this is something we know from thermodynamics. What else do we know? The first law of thermodynamics that states that the internal energy of our thermodynamical system may be changed either by heating or cooling the system, or by doing some work on the system, or when the system does some work. And this is simply energy conservation law. So we have some energy in our thermodynamical system, and in order to change it, we either need to add it to the system, for example, by heating the system, or we can do some work on the system, and again, this will lead to the increase of internal energy. Or the system, it may cool down, and then the energy will decrease, or it may do some work, and then the energy of the system will decrease as well. So simply, energy conservation law expressed in thermodynamics terms. And particularly for gas may only does work by changing its volume, either by compressing or by expanding. If it's compressed, then the work is done on the gas. When it's expanded, then the gas does some work. So the increment of work can be expressed as the pressure times the increment of volume. Again, this is equation from high school. This is the only way how the gas may work. So the solids may work in different manner, but we're here considering just gas thermodynamical systems. And now the second law of thermodynamics, which is much more mysterious and in some sense uninterpretable. So in general formulation states that the increment of entropy of our system is larger or equal than the increment of heat over the temperature. So this formulation is a bit hard to interpret. The more familiar formulation is following. If there's no heat exchange, if the system is fully isolated from the environment, so then dq equals to 0, so there's no heat exchange, and then the entropy may only increase. And I think you are all familiar with this basic formulation of a second law of thermodynamics. By the way, this second law has many philosophical consequences. For example, it defines us the error of time. So due to this law, we are able to distinguish past from the future. So past is just a situation where entropy was smaller, and future is a situation where entropy will be larger. When the system reached its equilibrium state, the entropy is at maximum. And starting from this point, we are no longer able to distinguish past from future. So there's no error of time anymore, because the system does not evolve. So it keeps fluctuating, but nothing changes globally. And from this point of view, we may say that the system is dead, because nothing is changed. So when the system is at equilibrium, then this inequality becomes equality, and then we can express dq as t times ds, and obtain this formulation of how our mean internal energy may change. So this is the combination of first and second laws of thermodynamics. Okay, so this is just a small illustration. So imagine that this is a completely isolated system, so no heat exchange. Its volume is fixed. This is initial configuration of the molecules, and it starts evolving. And it evolves according to maximum entropy principle. So until it reaches some equilibrium state where the entropy is at maximum. So this corresponds to the uniform distribution along this volume and some specific distribution of the momentums of the variables. And I think that you all agree that this is very natural evolution. And the system may evolve from initial configuration to this one, and after it reaches this configuration, nothing will change anymore. So there's definite change in the beginning, but after the system has reached this uniform distribution, all global evolution stops. So this means that the system reached its stationary state. Okay, so now let us return back to this equation that the increment of mean internal energy equals to TdS minus PdV. And now suppose that in our system we manage somehow to fix the entropy and the volume. This means that ds is 0 and dv is 0, because both entropy and volume do not change. And immediately from this equation, it will mean that at the steady state, the increment du bar will be 0 as well. So this means that mean internal energy will take extreme values, either maximum or minimum, and empirically we know that it corresponds to the minimum. And this is characteristic of one of the characteristics of the stationary state, given that we somehow managed to fix entropy and volume. This is a bit exotic formulation because it's not so easy to fix the entropy. However, immediately from this equation, we may write down more interesting properties of thermodynamical systems. So now imagine that we have fixed temperature and volume. This is much more realistic formulation because it is very easy. Imagine a gas in the balloon. Balloon has specific volume, and this balloon is placed in the thermostat. So the temperature is guaranteed to keep at the same level. So this is very realistic setting. And now consider what happens whether we are able to write down some objective that is minimized when the system reaches its stationary state. And this objective is called Helmholtz free energy, and is defined as follows. So this is simply mean internal energy of our thermodynamical system minus temperature times entropy. And really, if we consider its differential, so this is a differential of U bar minus differential of the product Ts. So then we may split the differential of the product according to product rule and obtain TdS minus SdT. Then we can expand the expression for du, which we already know. This is TdS minus PdV. Finally, two terms will vanish, and we end up with a minus SdT minus PdV. And this is exactly what we wanted, because if we fixed temperature and volume, this means that dt is 0, because temperature doesn't change. dv is also 0. And this means that our free energy, so U minus Ts, will, during the evolution of our system, will be minimized until we reach stationary state. So in other words, our system evolves, so our rho distribution evolves in time until we reach stationary distribution. Stationary distribution will not evolve anymore. And stationary distribution will correspond to the minimum of this value among all possible distributions rho z. So we know what objective is minimized when system reaches its equilibrium state, when T and V are fixed. And this is just, yes, and surprisingly, we also know the solution. So if we minimize this expression with respect to all possible distributions of ρ, we know that its arg minimum will be given by this expression known as Gibbs distribution. So what is here? This is just normalizing constant that ensures that this is a correct distribution, correct density function. Exponent minus energy of configuration Z over temperature. And depending on the value of temperature, this distribution may have different properties. So this is just one illustration for illustrative purposes. So here, imagine that this is a balloon of fixed volume in the strong gravitational field, and imagine that the molecules are also pretty heavy, so they're impacted by this gravitational field. And this is the example of a stationary distribution. So let us return back here. Let us look at this equation and imagine that T goes to 0. What will happen then? Then our system will evolve to such distribution where this internal energy is minimal, right? Because the second term can be skipped when T is 0. And in this picture, this would correspond to the situation when all molecules would drop down to the bottom. So if the temperature is 0, all our molecules will be at the bottom. On the contrary, if T is very, very large, then we may neglect the first term, and the minimization of free energy will simply correspond to the maximization of entropy. And in this case, in this fixed volume, we'll just have a random distribution, just have a uniform distribution of molecules. So these are two extreme cases. When temperature is somewhere in between, we get something like this. So this is not distribution where everything is at the bottom. This is not a uniform distribution. This is some specific distribution, which is fully described by this equation. And the particular shape of this distribution depends on the T. So in some sense, we may say that the temperature plays a role of balance between internal energy, which we would like to minimize, and between entropy that we would like to maximize. So there's a competition between those two forces. So physicists know this very well. This is universal law in some sense. And temperature balances their interaction. So pretty nice, although still not clear how it's related to deep learning. And next one, another very realistic formulation. Let us fix the temperature and the pressure. Not the volume, but the pressure is fixed. So it's easy to imagine, just imagine the cylinder and the piston. So the piston may move up and down, so the pressure is constant, but the volume may change. Can we write down some objective that is minimized when the system under these conditions evolves to a steady state? And the answer is yes, we can, and this is known as the Gibbs potential, and it's given by the following equation. So mean internal energy minus the product temperature entropy plus pressure volume. And again, if we write down this differential, few lines of algebra, and we end up with this expression. So it depends on dt and dp. And this is exactly what we wanted. When we fixed both t and p, then at the steady state, our differential of Gibbs potential is 0. This means that our Gibbs potential is minimized under this setting when we fixed temperature and fixed pressure. So this is the example of how it works. So again, the system evolves from some initial state to the stationary state. And during this evolution, the volume may also change, but the pressure remains constant. And during this evolution, this Gibbs potential that can be written down in an explicit manner is minimized. So this is, I think, almost everything we need to know from thermodynamics. So just to recap, if we are interested in describing the evolution of our thermodynamical system to stationary state under some fixed microscopic variables, so we may consider different potentials, thermodynamic potentials, depending on what microscopic variables we are fixing. So if we fix entropy and volume, then this is mean internal energy that is minimized. And minimization, of course, happens with respect to a distribution. So our system evolves, our distribution rho of z changes until it's reached stationary distribution. So if we fix temperature and volume, this is free energy that is minimized. If we fix temperature and pressure, this is Gibbs potential, and so on. Okay, and now what is the relation with deep learning? So imagine a relatively simplistic setting when we have deep neural network that is trained using stochastic gradient descent with a fixed learning rate. Then the update of our weights is given by the following equation. So the new weights equal to the previous weights minus learning rate times the true gradient of our trainer loss plus the gradient from weight decay plus some noise. The noise happens because of the stochasticity in our optimization procedure. So what do we know about noise? First of all, it has zero mean. So our stochastic gradient gives us unbiased estimate to the true gradient. And it has some variance, and the variance defined first by the variance of the stochastic gradient itself. So this is sigma squared. And this variance depends, for example, on the size of a mini batch. So the larger mini batch we are using, the smaller will be this sigma squared. But for now, we will suppose that this is some fixed constant, that we have fixed mini batch size, so sigma squared is constant. And by the learning rate, and it's proportional to the learning rate squared. So this is the update equations for SGD. And it's relatively easy to show that those updates correspond to the discretization of the following stochastic differential equation. Yes, sounds terrible. But fortunately, there's nothing too complicated here. So again, this is stochastic differential equation. What is important for us? So the first term is just standard differential equation. So here's the anti-gradient of our trainer loss and the weight decay times dt plus something stochastic. So dbt is a kind of random walk behavior. So that our trajectory will be stochastic. So this will be deterministic part, which tries to attract our thetas to global minima of our trainer loss plus weight decay. But we also have some stochasticity because of the noise in our stochastic gradients. And what is important is that the magnitude of this noise depends on sigma, that's okay, and on squared root of our learning rate. So this means that different learning rates define different evolution of our weights when we're using stochastic gradient descent. And by the way, if sigma is 0, for example, assume that we were using full batch gradient descent, then there'll be no stochasticity and we'll simply end up with a so-called gradient flow. But that's not our case. One more thing before we start the analysis of the behavior of deep neural networks. So we know that many deep neural networks contain normalization layers. And the normalization has many attractive properties, well, maybe not so attractive because it complicates the analysis of the behavior of neural network. But one important property is that due to normalization, our neural network becomes scale invariant. So if we consider our trainer loss function with the weights theta, if we multiply all thetas by some positive constant, nothing will change. So the neural network will remain the same because of normalization. So that's important. And this means that instead of considering the behavior of our deep neural network in the whole Euclidean space of weights, we can switch to a unit sphere. So we can establish variable u, which is theta over norm of theta. So the norm of u is, of course, 1. So this is a point on the unit sphere. And we can say that instead of trying to find the weights in the whole Euclidean space, we may simply try to find the equivalent weights on a unit sphere. Okay, but what happens with the weight norm itself? And it appears that there's a competition between, again, two forces. So if this is the current values of our weights, so there's a weight decay, which tries to attract us to the origin. But there's also stochastic gradient, which is always orthogonal to this beam. Why it is always orthogonal? Because along this beam, the function is the same. Because we may multiply our thetas by positive constant, and this means that we may move it either along this beam, and nothing will change. The function will remain the same. This means that the gradient should be always orthogonal to the level set. This means that when we move according to gradient or stochastic gradient, our weight norm may only increase. But we also have attractive force from weight decay, so there's a competition between those two forces, and because of this, the weight norm may either increase or decrease during the training procedure. So now we may perform this change of variables, and instead of considering the evolution of theta, we may say that theta equals r times u, where u lies on the unit sphere and actually defines the functionality of our neural network, while r is simply the norm of the weights. And then we may, instead of one stochastic differential equation, we may write two different equations for u and for r separately. I haven't written them down because they're a bit complicated, and actually it's not so important. What is important is that for u, we still have stochastic differential equation. For r, we will have ordinary differential equation. So there'll be no stochasticity in evolution of the norm of the weights of our neural network. And surprisingly, it appears that both differential equations can be solved in a closed form under some mild additional simplifications. And now let us consider a bit simplistic training protocol. Instead of fixing learning rate, let us fix so-called effective learning rate that is given by this equation. So this is learning rate over squared norm of the weights, eta over theta squared. This is, by the way, not our invention. So this training protocol was considered in some papers, some theoretical papers that were devoted to the studying of the training dynamics of our deep neural networks. And it has some specific sense. So I tried to illustrate it on the following picture. So imagine that this is the Euclidean space of our weights. This is the unit sphere. And we start our training process from this point, and our weights evolve according to this red line, and we end up somewhere here. But we may put in correspondence to this training process the equivalent dynamics, which is depicted by this blue line, which is actually lies on the unit sphere. Because well, the functional evolution of our neural network will become the same. Because to any point in our Euclidean space, we may put in correspondence the equivalent point on the unit sphere. Pay attention that here the weight norm changed. So here it was smaller, here it was larger, here weight norm remained the same. And what does it mean from an optimization point of view? So this is a similar picture but from a different viewpoint. So this is our weight space, this is our unit sphere. Imagine that we were somewhere here, and this is the slice of our training loss along this unit sphere. So if we're here, and we're trying to minimize our training loss, so our anti-gradient will be directed somewhere here, according to the tangent line. And now let's imagine that we have taken this point and increased all the weights in k times. Then we'll be somewhere here. So the point is the same. So the neural network is the same, but the weight norms have increased in k times. So we also have gradient here, but pay attention that the gradient became smaller here because the curvature of our function was reduced because we are moving along from the origin. So here the curvature was quite high and the gradient was also high. Here the gradient is smaller. But in order to move to equivalent point, so imagine that when we were in the unit sphere, by taking move along this gradient, we have moved from this point to this point. Then, in order to move on this larger hypersphere from this point to this point, our gradient is k times smaller, and we need to move k times larger, k times longer further to reach equivalent point. And because of this, if we want to repeat the dynamics on the unit sphere, we have to update our learning rate as following. So we take learning rate in the unit sphere and multiply it by k squared times. So now the standard protocol is when we fix our learning rate, and then our effective learning rate changes. But we may consider alternative protocol where we fix effective learning rate, and then our learning rate will depend on the squared norm of our current weights. So this is, again, quite important because it allows us to fix the resolution of our optimizer on the unit sphere, just removing the symmetry induced by scale invariance. Okay, so let us imagine that we have followed this protocol. Then we can solve both differential equations. And for the U, this is stochastic differential equation, so its solution will be stationary distribution. We'll end up with this stationary distribution. And it looks very, very similar to Gibbs distribution from thermodynamics, really. If we say that our loss function at a given value of U is just internal energy of our ideal gas in configuration Z, then effective learning rate times sigma squared will play the role of temperature. And we'll obtain exactly Gibbs distribution, or analog of Gibbs distribution in deep learning. So it appears that the stationary distribution under this training protocol will be given by this equation, where the train loss function plays the role of internal energy, while the denominator here plays the role of temperature. Okay, what about solving the differential equation with respect to R? So R is just norm of the weights. It appears that this differential equation also has a solution, and the solution is following, that we may start with arbitrary R, but after a while we will converge to this particular value. So during the training, our weight norm will converge under this protocol when theta effective was, when effective learning rate was fixed, we will converge to this particular value of our weight norm. Okay, and now let's combine these results together. So this is the expression for the R. We already know that effective learning rate times sigma squared can be interpreted as a temperature. So there's a temperature here. What about lambda? What about weight decay coefficient? Weight decay coefficient defines the strength with which we are compressed to zero. And in some sense, this is very, very similar to the pressure, because the pressure in the ideal gas does exactly the same. So it tries to compress us. It tries to reduce our volume. So we can associate the weight decay coefficient with the pressure, and then the remaining value, R squared, can be associated with the volume. And if we do this, then from this relation, which is directly follows from the solution of our differential equation for the weight norm, we'll obtain the exact analog of our ideal gas law. So pressure times volume over temperature is constant. Pressure is lambda, volume is R squared, and this is temperature. And the relation equals to constant. So this is pretty nice. And now let us see what else we can derive from this thermodynamic analogy. So remember that our current protocol is that we have fixed effective learning rate. This means that we have fixed temperature. We also train our deep neural network with a fixed weight decay coefficient lambda. So this is quite standard protocol. But lambda is pressure. So this means that our neural network is trained with a fixed temperature and pressure. And we already know what should be the objective that is minimized when our system evolves to equilibrium state. So this is Gibbs potential that is given by this particular equation. So mean internal energy, the product temperature times volume minus pressure times volume minus temperature times entropy. So it can be computed in exact way, and we can estimate whether this is really what is minimized during training of deep neural network. Or in terms of DNN, this corresponds to the following objective. So Gibbs potential is given by the expected value of our train loss, the weight decay, so lambda times squared norm of our weights, minus this amendment. So actually this is our train loss, which we are trying to minimize. So train loss plus weight decay. And this amendment is caused by the noise in our stochastic gradients. So again, if sigma were 0, for example, if we used full batch gradient descent, there'll be no this amendment, and the Gibbs potential would simply be the same as the loss which we are trying to minimize. But in practice, of course, so this amendment arises because we are using stochastic optimization. So this table summarizes the similarities, the analogies between deep learning and thermodynamics. So the distribution of the parameters of our particles corresponds to the distribution of weights in our deep neural network. The average internal energy corresponds to average train loss function. Temperature is just effective learning rate times sigma squared. Pressure is just weight decay coefficient. Volume is squared norm of the weights, and entropy is just entropy. Okay, this is one experiment on a real fully scale invariant deep neural network, which we tried to train using different fixed effective learning rates. And we see that depending on the choice of learning rate, the train loss is first it's decreasing, but then it stabilizes and remains surprisingly stable along by slightly fluctuating along some stationary value. And this value can be described by our Gibbs potential. So this is another illustration, again, experiment on the real deep neural networks. So what is shown here? Let us try to understand. So different colors correspond to Gibbs potentials computed with a fixed pressure and different temperatures. So the color corresponds to the temperature. So of course we can compute Gibbs potential for different temperature because it's explicitly depends on the temperature. Here, on the x-axis, correspond to different checkpoints, to different stationary distributions to which we have converged using different fixed effective learning rates. So these are the effective learning rates, and the point here corresponds to stationary distribution to which we have converged if we used this particular effective learning rate. And finally, the black stars correspond to the effective learning rate, which exactly corresponded to the given value of temperature. So for example, for this temperature, the corresponding effective learning rate was here. For this temperature, the corresponding effective learning rate was here, and so on. And we see that actually this is exactly the point where the minimum of Gibbs potential is achieved. Or in other words, this means that among all possible stationary distribution to which we can converge, the Gibbs potential for the corresponding temperature corresponding to this particular effective learning rate is really the thing that is minimized. So for all other stationary distributions, Gibbs potential will be higher. Or in other words, this is experimental proof that this is really what is going on when we train our deep neural networks with effective learning rates under the condition that the neural network is fully scale invariant. So instead of minimizing the train loss, it minimizes the Gibbs potential that depends on the temperature, which is defined by the selected effective learning rate. This is two-dimensional picture. This is already illustration on some artificial example, where we also try to minimize some scale invariant functions using stochastic gradient descent. And we changed here both the pressure or weight decay coefficient and the effective learning rate. And again, we see full correspondence. So each subplot here depends Gibbs potential for a given value of pressure and temperature. And along the individual subplot, we see the values of Gibbs potential computed for different stationary distributions with this particular effective learning rate or temperature and this particular pressure. And the red star corresponds to the situation when the effective learning rate and weight decay coefficient were exactly the same as the values used for computing Gibbs potential. So again, this means that if we fix some effective learning rate and weight potential, there exists some function that is minimized during our training, and this function is given by Gibbs potential with the corresponding temperature and pressure, or effective learning rate and weight decay coefficient. And now let us consider a bit more standard training protocol when instead of fixing effective learning rate, we fix just learning rate. What does it mean? Remember that learning rate is given by effective learning rate times squared norm of the weights. We already know that effective learning rate is directly proportional to the temperature, while squared norm of the weights, this is exactly volume. This means that this is pretty interesting protocol when we fix the product of temperature times volume. And we have consulted with the physicists, asking them, guys, have you met such protocol in real thermodynamics? They don't know. We've never worked with such interesting conditions. So if we train our deep neural network with a fixed learning rate and with a fixed weight decay coefficient, as always. This means that we have an analog of thermodynamic system which evolves under fixed pressure, weight decay coefficient, and fixed product temperature times volume. So this seems a bit strange from physical point of view, but this is possible. So this is physically possible process. And this means that for this process, we may derive the necessary differential equations which describe the evolution of both the volume, or R squared, and the evolution of our distribution on a unit sphere. So we end up with those answers. So this is the limit value where our weight norm converges to. This is the stationary distribution along the unit sphere where we're converging. So again, L of U plays the role of internal energy. And then the remaining part plays the role of 1 over T, 1 over temperature. So then we can formally redefine temperature as follows. And again, if we substitute it to this equation and interpret R squared as volume and lambda as pressure, we'll obtain this relation, which is exactly equivalent to the ideal gas loss. So that's quite interesting. And it was surprising because it's surprising not only for us, but mainly for physicists, because physicists have not expected that. They thought that ideal gas equations were derived from different considerations under the assumption that molecules do not interact with each other. Is it the same situation in your deep neural networks, they asked us. But no, in our case, our weights do interact with each other. And the change of one weight changes the behavior of other weights as well. So this was completely different initial assumptions, but surprisingly, we've got the same analog of ideal gas law. And finally, for this training protocol, where we have constant pressure and we have constant product of temperature times volume, from thermodynamical perspectives, we can derive the new objective, which is minimized under those constraints when the system evolves to stationary state. It has a bit exotic form, so I have not written it down here, but it exists, and experimentally we see that this is really what's happening when we perform such kind of training. When we try to minimize our train loss using SGD with a fixed learning rate eta. So I think that this is a point where I will stop. So the talk was, maybe a bit heavy, but again, do not worry if you miss some details. Numerous equations here were mostly for mathematical correctness. So my main point was to present you the concept that there are many analogies in deep learning and in thermodynamics. And that's important because thermodynamics is much better studied discipline than deep learning. And we can acquire many results from thermodynamics, like Maxwell relations, which I haven't covered, but they exist, and apply them to derive similar results for deep learning. And of course, this is just first steps towards this direction, and the obvious directions for the future work is first, relax the assumption that the noise of our stochastic gradients is isotropic. This was this assumption based on which we've derived the differential equations. Include small number of non-scale invariant parameters, because again, in the real state of the deep neural networks, not all parameters are scale invariant. There exists some relatively small part of parameters that are not. And it's very interesting what happens if we include those parameters into our model. My hope is that we'll end up with a real gas law instead of ideal gas law. We'll end up with a real gas law with these van der Waals isotherms, which serve as amendments of the ideal gas law under some more realistic assumptions. So maybe we will derive something like this. And of course, it's interesting to see what happens if we switch from SGD to more advanced and perspective optimizers. But these are just directions for the future work. So thank you very much for your attention.
This is quite interesting. When you train with fixed effective learning rate. If I got it right, it means that you need to normalize your learning rate. Like, how do you implement it? It means
we know the
norms of the weights?
yes, of course. So we take just the current weights. We compute its norm, and we renormalize our learning rate. We divide it by the squared norm of the weights, and so we obtain the effect. So you're asking when we fixed effective learning rate, how we need to update the learning rate. Yes. So we take this fixed effective learning rate, we multiply it by the squared norm of the weights, and we obtain the learning rate with which we need to make the next step.
And
so the problem is that learning rate in this setting, learning rate will be changing constantly.
Yes. So it's kind of a new learning rate schedule in a way, right? So for this new schedule, you have seen this nice, lost charts. Which one was that? The next one? Yeah, these ones, which are kind of expected from physics, and we also see them in deep networks. So that's the result.
Well, actually, we see pretty similar plots even if we fix just learning rate instead of effective learning rate. We also see the stabilization of the train loss, but this stabilization is just described by a different objective. So this is not Gibbs potential, but we need to derive different objective, and this is why I started from this non-standard setting when we fix effective learning rate, because in this case we have direct analog in thermodynamics. This is Gibbs potential. And when we fix just learning rate, we'll have to derive some different objective with some different thermodynamic potential, which is possible, and we did it. But again, it has a bit complicated form, so I have not written it here.
I see. So, and did you look how the actual learning rate changes when you fix the effective learning rate?
Yes.
What's it? Is it like going down or going up, or?
Let me check. Let me remember. Actually, I think that we can maybe derive it from the equations which are already here. But in general, it just evolves something like this or like this. So
I see, okay.
From initial value to some value where it will stabilize.
And my next question is, in practice, we now always decay the learning rate to 0, right? So
yes.
Could it correspond to another physical process? Although
yes, of course, it will correspond to another physical process. Again, just for simplicity, let us imagine that we're decaying not the learning rate, but effective learning rate.
Okay.
This means that we are just decaying the temperature in our thermodynamical system. And here, by the way, this is a very interesting question, because imagine the following situation: that again, you have deep neural network, you have SGD optimizer, and you start training your deep neural network with a quite small learning rate until you reach convergence. Will you have a good generalization ability? Will you have good validation accuracy? The answer is no. You can do much better if you start with a large learning rate and then gradually decay it. Why so? Because in this case, you need to carefully decay it. So if you decay it too fast, you again will end up with a suboptimal point where your train loss is at minimum, but generalization is pretty poor. So you need to define it relatively slow. And this theory provides us the constructive way of understanding at what moment we can already decay our learning rate. So let me return to one of the first pictures. Yes. So imagine that this is the plot of our train loss when we minimize it using fixed learning rate. So after a while, we need to perform learning rate decay or perform annealing. But at what moment should we do it? Should we do it here, 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 or here? Of course, well, we can do it, for example, here, but we see that on this interval, nothing is changing. So we could do much better, computationally much more efficient, if we performed learning rate decay here. Or, of course, we could do it here, but again, this would be computationally suboptimal. But if we do it here, we have not yet converged to stationary distribution with a given learning rate. So the good rule of thumb could be fixed learning rate, wait until you have converged to the stationary state, then a new learning rate. Again, wait until you have converged to the new stationary state, then anneal it again. So you shouldn't anneal it too early, because in this case you will get suboptimal performance. You should not anneal it too late, because in this case you'll get computation inefficient scheme. And this theory allows us to detect the moment when our neural network has reached the stationary state under the fixed learning rate.
Interesting. I think in practice now we keep the learning rate at some level, although it's not SGD, right? It's usually Adam. We take it this warm-up stable decay schedule, right? We go with stable as long as we have compute or data, and then only in the last 10% we decay. And I think in this stable phase we always see, we don't really see loss convergence, right, nowadays with LLMs and others. It's
yes, but you are using different optimizer, because Adam is an extremely tricky optimizer that has many self-adaptive elements. So this is why I mentioned it as a direction of future work. I'm interested myself by a lot of what happens when we switch to Adam. But the analysis of this behavior is much more complicated, so we need to start from
it's a different physics, right?
Yeah.
Okay.
Exactly.
So questions, Michal?
Yeah, thanks for the talk. So from all the connections, do you see what we should be doing differently to arrive to better results? What kind of, how we should be changing, algorithms, how we should changing the training set, how we should be learning rate to get better algorithms, right? From all these connections, do you have, ideas maybe?
I see. I've got your point. That's the question I'm asking myself constantly.
So I have then another question. Do you see in what we do currently that we do something that doesn't make any sense, completely nonsense things physically, and then we should really think that, okay, this is completely stupid and that's opportunity to improve?
Well, I would say that this theory, again, provides us some intuition of how we can, for example, manage the learning rate schedule. And we can check whether the existing learning rate schedules are efficient or not. Efficient in terms that for any current learning rate, we need to first reach equilibrium state and then perform annealing.
Yeah,
so we can check.
Yeah, it's not published, but I know that some labs actually are doing already what you're suggesting. Empirically, not by knowledge of physics, but empirically, people discovered. And semi-theoretically, you're probably familiar with like mu-p or mu-on optimizers, right? Also, does that, which is currently very much used, right? Like, does that or is that explained by something in physics? Because it's another adaptive Adam-like optimizer, even more adaptive, even more difficult.
So instead of Adam, you should focus on mu directly.
Yes. That's very interesting, and again, I'm looking forward to the moment when we start studying the behavior of mu-on and Adam, and I do hope that we'll understand that this particular scheme of mu-on or Adam corresponds to something in thermodynamics. Maybe this will happen, that this is something reasonable from physical thermodynamical point of view. I don't know yet. So currently our work is at the stage, so the most important what we have achieved is we managed to build this thermodynamic analogy. How it can be used, this is still an open question.
I see. Please.
One thing I was up here.
Yeah.
Sorry, I was already given the mic. So one thing I was wondering is, if I'm taking a thermodynamic analogy, if you can know what your Gibbs free energy of your optimal state is, then you sort of have an estimate potentially of either the activation energy or the total cost to going from your current state to that final state, right? So is this sort of analogous to something related to the compute budget or the total number of calculations that need to be done to go from, say, your current state of model with its weights to its optimum state? And therefore, maybe the next question would be, is there any way to estimate the Gibbs equivalent energy of your optimal state such that you could very quickly determine how far you are away from actually your optimal state?
Great question. still an open question. So unfortunately, I cannot comment on that. But this is definitely the direction we should think over.
Thanks.
Sorry. I think quite an important thing here is that you stated initially that we are talking about scale invariant neural networks.
Yes.
Yeah. So, and I'm quite curious, like if I remember it correctly from your and some other papers, your statement is like in experiments you say that neural networks with quite a lot of batch normalizations are scale invariant enough. So I have like first of all, I am curious if did you measure somehow how far like your kinda scale invariant neural networks in your experiments are far from really formally scale invariant? And second question, kind of the same, are our real neural networks from our real life, how far they from being scale invariant? So can we expect somehow this theory to be related to our real networks or not?
Well, this is actually what we are working over right now. So the only thing I can say you right now is that qualitatively we observe very, very similar behavior. So if, for example, we consider deep neural network where we have normalization layer after normalization block after each layer except the last one. So this is quite typical architecture. We see very simple behavior. So something very simple to Gibbs potential is being minimized. So I suspect that just small amendments of the Gibbs potential or of this ideal gas law are needed. Just like we switch in physics, we switch from ideal gas to real gas. So for real gas, we have a bit different equations. They look pretty simple, so they're just like ideal gas plus some amendments. So I suspect that this is the case here as well, because we observe very similar behavior. I cannot guarantee that it is exactly the same. We do not have yet tools to measure the difference. So I suspect that it's a bit different, but just a bit.
Please.
Thank you for the talk. I think I have a question that kind of corresponds to the one asked previously. So one, another parameter, you varied learning rate and of training process, but another parameter that you can vary is the amount of parameters in a neural network, which would correspond to a number of molecules in our ideal gas, which we don't usually count in thermodynamics, but in neural networks we do. And do you think there is a thermodynamic analogy between increasing the number of parameters in neural networks? Because if we do, then we would have a thermodynamic scaling law for neural networks, which were quite hunting for a few years.
I see. Well, first of all, this is not exactly right that we do not have this the corresponding process in thermodynamic. We actually do. And there's a so-called chemical potentials that define how the behavior of the system changes when we increase or decrease the number of molecules in the system. So the physicists explore such things as well. So we were thinking about that, and maybe this will be one of our future steps. But there are too many open questions how to change the number of parameters. So we can, for example, increase the depth or increase the width or do something else. So there are too many degrees of freedom, and I'm afraid that different degrees of freedom will have different behavior, different scaling behavior. But this is, again, quite nice direction for future work and maybe for a separate PhD thesis. So thanks for pointing out. And guys, I just want to say sorry that for many of your questions, I'm just answering that this is a good direction for future work, not because I'm an idiot, but just because these are results which were obtained just a month ago, 2 months ago. So these are very, very fresh results, and of course, this is still work in progress. But please do continue asking questions. Okay. So maybe there'll be some questions for which I'll be able to answer.
Thank you very much for the great talk. I wanted to speak about a bit on the tail end of the future work. Assuming that this works for muon, ADAMW, or other fancy optimizer, doesn't really matter, and there is some exact correspondence of hyperparameters of Adam and other optimizers to a thermodynamic system in ideal gas or real gas system. Would this exactly mean that we would be able to predict the ideal hyperparameter space that would lead us to the best possible convergence for an LLM? Essentially, I'm just trying to derive, like, let's say everything works, what we can get out of it.
I fully understand, and as I thought, I'm constantly asking myself, because now we have very elegant analogies, but too few practical consequences. So I'm only guess that, of course, it would be very great if we manage somehow to find the relation with the generalization ability of how well our neural network trained under a specific protocol will behave on the validation data.
I mean, because in your slides, when you were showing the losses under different fixed hyperparameters of learning, we were able to say, yeah, this leads us to a better convergence rate for the neural network. Assuming it can be done for other optimized. Assuming it can be done for other optimizers, we can essentially say, yeah, we can find the latest and greatest set of hyperparameters, at least their learning rate that is better than the LLM.
Well, at least up to our current understanding, we have played with such scale invariant or almost scale invariant networks multiple times. It allows that the optimal strategy in terms of achieving the best possible generalization is when you first train until convergence here, then until convergence here, here, and here. So, well, maybe this is something trivial, but what is important that each time you need to obtain convergence first to stationary distribution and then to anneal learning rate. So if you do not do this, you will converge, but your generalization will be worse than it could be. So this is, at least for now, one of the practical consideration that we can derive from this theory.
Yeah. Thank you very much.
Thank you. I have two questions. One, what are your thoughts about doing the inverse process? So here you started from the neural network, from the optimization problem, and then derived the equivalence in thermodynamics. What about doing it inversely, starting from the thermodynamic equations or any physical dynamics like heat equation, wave equations, and get back to get the corresponding neural network? Maybe here we can find some more optimal optimizers and set of parameters. And the second question, if we have such correspondence, why can't we do training in analog? Instead of digitally training models on GPUs and stuff, we can, for example, construct a physical system which corresponds to that network and that optimization and operate that physical setup. Thank you.
Well, for the second question, this is, I think, potentially possible. Again, the question, what particular problem are we going to solve if we use this analog physical system? It just reminds me the model of world economy using just water pipes in one of exponent in one of British museums. So you can do this. This will be analog model, but I'm not sure that it will be helpful, at least in solving particular problems. Maybe it will be helpful in understanding better the dynamics of the system. So as for the first question, well, maybe. So currently, what do we understand? We understand what is pressure in deep neural network, what is volume in deep neural network, what is temperature in deep neural network. So maybe using these understandings, we can really consider some different processes known in thermodynamics like heat equation and try to build similar processes in deep neural networks and see what they correspond to. So this is probably possible, but again, we still have not had time to do that.
More questions? No, I'm not very devagar.
Can you? So thank you for the talk. I wanted to ask, how are the stochastic differential equations derived? Or more like, what are the underlying assumptions?
So you mean this one?
Yeah.
Probably. The underlying assumption is that the noise of our stochastic gradient is isotropic, so with respect to any direction, and is constant with respect to the change of a point in our weight space. So for any point in our Euclidean space of the weights, the variance of our stochastic gradient is the same, and it is isotropic. So this is, of course, simplification. And again, this is something we are working over right now. But our experiments with the real deep, that of course they're not so real, but at least these are scale invariant deep neural networks, show that they exhibit very similar behavior that is in full correspondence with the derived theory, although we cannot guarantee that the noise of stochastic gradient there is isotropic. But this is main assumption that we have made along with the scale invariance.
Okay, so
thank you.
Last question.
Thank you for the talk. I'm here. First of all, I would like to know where and when to expect the publication of these results. And secondly, I have a question regarding your... Sorry, do you hear me now?
Yes.
And I would like to know about your insight. Like you said about the between ideal gas, right? So in ideal gas, the particles do not interact with each other, and you claim that taking into account some interactions, I thought that you are referring to van der Waals-like interactions, like maybe maybe they give better results in like linking the analogies between these physical systems and the neural networks. Did I get it right, or I am maybe missing something?
Well, again, this was just my hypothesis that we'll need some corrections of this theory when we start considering more realistic settings when not all parameters are scale invariant. So if anything is scale invariant, and if the noise from stochastic gradients is isotropic, this will be exactly the equations we have derived. So this will be ideal gas. But in practice, of course, we don't have these idealistic neural networks, so we have something that is not scale invariant, and the noise is also not isotropic in general case. So, and I think that the taking into account those effects, under assumption that they're not too crucial and they do not destroy the whole theory, will lead to the amendments of our equations, and that we'll have, instead of ideal gas, we'll have something, not exactly the real gas model by van der Waals, but something conceptually similar. And regarding your first question, I haven't quite heard. So what was the question? When and where?
When and where to expect the publications of these results?
Well, we're currently preparing the submission. We probably will not be ready to ICLE deadline, so we're planning to submit it to ISTATS as a bit more theoretic conference. And after we submit it, we of course publish it on our archive. So this will be in October.
Okay, thank you very much.